Okay, I wanted to give you a little help on this homework problem number 7 from lesson 1-8. We're talking about linear programming. And so let's just take a look at what this problem is, the information that's giving us and what it is that we're supposed to do. So we have this package delivery service, and there's a truck that can hold 4,200 pounds. Okay, so let's keep that information in mind. We have a maximum of 4,200 pounds that the truck can haul, and in terms of cubic feet, it's a maximum of 480. The next sentence tells us something else that's very important. Deliveries will only be made if there are at least 10 of each type of packages. Well, what are our types of packages? We look down in the table and we have a standard package type, and then we have an oversize. Okay, so just reading through the 4 parts of this problem, kind of looking at the information that we're given, the first thing we're supposed to do, letter A, is write the constraints. And again, think of that as the limitations or the most we can do based on the equipment that we have. You know, again, we don't live in a perfect world where all of our resources are unlimited. So we are constrained by certain things like the size of a truck and how much it can hold. Those types of things. So we're going to represent these constraints that we're given in terms of inequalities. But first, we have to identify what our variables are going to represent. And again, there are 2 types of packages. And in these linear programming problems, that's always going to be the case. You're going to have 2 different products that you're going to be defining with variables. So I'm just going to take the first one. X will be the standard size, I'll just call. And again, this is the number of packages. I want you to understand that too. We're talking about a number of packages because letter D says determine the number of each type of package needed per truckload to maximize revenue. So that's the end goal, is to determine how many of each type. So that's what our variable needs to represent. All right. So I don't want you to think that this is X is the weight of packages. It's the number that are delivered, number of standard. We'll just put it like that. We understand that these are being delivered, but here are the number of standard delivered. Y will be the number of oversize. Okay, so with those variables defined, let's go ahead and come up with our system of constraints. Let's use a brace here to represent the entire system. So I'm just going to start off with this idea. We talked earlier that there is an implied constraint that we never make negative quantities of any product. Well, that's not really going to be needed here because we're told that at least 10 types of each package, at least 10 of each type of package has to be delivered. So let's just start off with that constraint. X has to be, the number of standard has to be greater than or equal to 10, and then that's also true for Y. The number of oversize has to be greater than or equal to 10, or else we don't deliver. Okay, so we got that out of the way. Now let's do a constraint. Since we're given the maximum number of pounds and we're told how much each type of package weighs, or at least a range of how much they weigh, then that clues us in that that's going to represent another constraint. So for the standard, they're up to 25 pounds, so 25 pounds for each standard, and then added to that up to 50 pounds for each oversize, and that cannot go over, cannot exceed 4,200. So what we're doing here is basically defining the maximum. Okay, and then let's do another constraint in terms of volume, because it's kind of a clue. They give you the total cubic feet, that's in volume, a reference to volume. And then we're given the volume maximums for each package type. So kind of like we did here, up to 3 feet cubed for each standard up to 3 cubic feet, or 5 cubic feet for the oversize. Combined, it cannot exceed 480. Okay, and so that's it. That's our system of constraints. And again, because if you notice, they say if they are at maximum weight and volume, so that's why we used 50 for the upper limit for oversize, and then 5 for the cubic feet for the oversized. Okay, so we're going to do letter B on the next slide. I've got a graph ready to go, but we're just going to get our information ready first. So letter B we'll take care of in just a minute. Now letter C says write a function to represent the revenue per truckload. All right, so revenue, that's money. So let's go to green for revenue. So it's a revenue function, so I'm going to use the letter R for revenue. And we're going to be inputting variables for X and Y, which represent number of each types of package. And we're told that we're going to make $12.50 for each standard package. So $12.50 times the number of standard packages delivered. And then we're going to make $20 for each oversize package delivered. And so there's our letter C. That's our revenue function. And then letter D, after we've done our graph, we'll come back and we'll come back to this slide and take care of letter D. Okay, so I just went ahead on the next slide and I put a graph, and I used the same graph type that you're using for your homework. So hopefully that'll cut down on some confusion when we're using two different types of graph paper with different grid lines. Sometimes I understand that can be a little confusing. So let's take a look. I just went ahead and recopied this for us here, kind of color coding it so we can do our boundary lines and shading accordingly. Or I'll probably just do the shading all in one color, but at least we'll do the boundary lines in these colors. So let's take a look. Let's take a look first. Remember, you should always label your axes, however they're defined. And we define the x-axis as the number of standard packages. These graphs do not make any sense if you don't label these axes. Delivered. And then the y, we will say number of oversize. Delivered. Okay, and now let's go ahead and see if we can determine what our units are going to be made in. So what I would do is just go ahead and figure out, we're going to be doing graphing by intercepts. I think that's easier to do in cases like this. So let's go ahead and find out what our intercepts are and look at the largest ones, and then that'll kind of guide us into how we need to make these and in what unit these grid lines need to be made so that we can graph the whole line, both intercepts. So obviously we got x is 10, y is 10, no problem there. If I do the blue, remember to get the x-intercept, you just divide 25 into 4,200. So let me just come over here, and if you divide 25 by 4,200, that's going to be 168. All right, so that's the x-intercept for the blue. So let's just jot some stuff down here. So the blue will have an x-intercept of 168 and a y-intercept. So to get the y-intercept, just divide 4,200 by 50, and that's going to be that's going to be 84. So all I'm doing here is just identifying what the x and y intercepts are, so I can get a feel for what the units need to be on each of the axes. All right, so that takes care of the blue. Now for the green, same thing. So let's see, the x-intercept, pretty easy. If we divide 480 by 3, that's going to be 160. And the y-intercept, if we divide 480 by 5, that's 96. Okay, so looking at what we have, and I believe we have 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, at least 9 visible. You could probably think of 10 if you went to the end of the arrow, but let's just think 9. Well, obviously, if we did, for example, 10s, that would get us to 90, and that's not going to be enough. So if we do 20s, all right, 20 times 9 is 180, and that would give us plenty to get these two bigger x-intercepts graphed. And so we're going to settle on setting our units up in terms of 20s. And so you can just do this, you know, and I would always recommend, most of the time I think it's easier if you do both in the same. It's not required, but I think in this case it's definitely easier. So both my x and y axis, each one of these grid lines is 20. All right, so let's graph our minimum number of packages constraint. The x is greater than or equal to 10. So you'll have your ruler, and I'm going to set up my line draw. We're going to do these in red. All of these are going to be solid. All right, so we're going to estimate 10. X equals 10 as the boundary line, so I'm going to say, well, I'm going to hope that that's halfway between 0 and 20. It's pretty close. And then y equals 10 will be this way, horizontal. That's a little high. Let me try that again. It's not easy to do with this thing. That's pretty close. Okay, so, and we're going to be greater than both, so to the right and above. So basically, so far we're shading above and to the right of those two red lines. Okay, now let's do the blue. And again, here are our x-intercepts. So we have an x-intercept, or x and y-intercept. X-intercept of 168, so 1, 2, 3, 4, 5, 6, 7, 8 is 160. 20 times 8 is 160. So we just need to go a little bit further. And again, it's a guesstimate. We'll get exact. We'll use algebraic methods to get exact as far as where the points cross if needed. But for now, we're going to do our best guess. And it should be just a little bit to the right of that 8th grid line. And then the blue y-intercept is 84. And again, that's up 4 and really just a little bit higher. I'm just going to estimate just a little bit more. This one might be a little bit too far, but again, it's our best guesstimate. Okay, and oops, erase that. And now we'll line those 2 points up. With your ruler, it's pretty easy to do. Not quite so easy for me, so I'll do my best to hit those 2 points. That's pretty good. Okay, so we're saying that that is the constraint line for the blue. That was the weight constraint, and then this is the I forgot already, the volume, sorry, the volume constraint. So we'll do that one in green. Okay, so for the green we have a x-intercept of 160. That's nice. Just go to the right 8. And so we're real close. And then we're going to go up 96, which is just right below 100, of course. Just a hair underneath 100. And let's connect those, and I'll do this one in green. All right, I think we got all of our boundary lines drawn. And now we just have to think about the shading. We've already said that we know we're going to be shading above and to the right of the reds. And for the blue and the green, we're doing below for each. Okay, below the blue, which is under, and below the green. Okay, so what we're saying then is where we're below for both, there's a point of intersection, and we're going to have to figure out exactly where that is right here. But beyond that point of intersection, we would be shading above the green. And so the only place where it is or exactly below both, it would be in this area. Like that. Do this. Right. So below both the blue and the green. Okay, so remember this shaded area that I've shaded in yellow has a name in these linear programming problems. We have identified what is known as the feasible region. Come down here since we don't need any area in this third quadrant, just so you can see that term again. So the yellow is the feasible region. And it's from the feasible region that we get vertices, and those are points of intersection of two of our constraint lines. And I'm going to circle them, and then we're going to talk about how we find out exactly where they are. So this is really kind of blended together. I'm going to say it's about right in there, but we're going to figure out exactly where that is. And then we have this one right here. Now it's where the green hits the red, not the blue, because again, we're only talking about points of intersection on the outer edge of the feasible region, and the blue hits the red beyond the shading. So let's first of all just go ahead and take care of the one vertex that's pretty obvious. Okay, right here. We know that this has to be the point 10, 10. Okay, so I'm just going to start listing vertices, and there's 4 of them. So 10, 10 is pretty obvious. The others, not quite so much, but here's what you can do. You're basically resorting back to solving systems of equations. Okay, don't let these inequalities throw you. Those are for the shading purposes. But if we take, for example, if we want to know where red and blue cross, which I do because that's important to know, then I just take this as an equation. Okay, so instead of x greater than or equal to negative 10, let's say that I said it's equal to 10. And then I take the blue in its equation form. 25x plus 50y equals 4200. Okay, and so go back to one of your methods. In this case, obviously substitution makes sense because we already have a variable defined. So substitution says solve for a variable, well, that's already done, and then replace that variable in the other equation, and we can find out what the y is. We already know what the x is. This will help us find the y. So we plug in 10 for x, and I'll just cut to the chase. I think you know how to solve for y. You're going to subtract 250, divide by 50, and you're going to get y is 79. Okay, so that's this vertex right here. It's the point 10, 79. And just for space purposes, I'm going to erase this, but I just wanted you to see where it came from and how you get these points of intersection when the graph really doesn't tell you for sure. I mean, we have a ballpark, but we got to be exact. Okay, let's take a look at this one right here. Well, that's the intersection of the green line and the blue line. All right, so once again, you can just think of these as equations. We've already taken care of the shading, and if we want to know where two lines, it's supposed to be 42. If we want to know where two lines cross, then we can use an algebraic method to tell us. And I'll just keep it blue instead of changing it, but you see what I'm doing here. I'm just taking the blue equation and putting it with the green. And here's a system. And then you just pick a method. If these were already solved for y, sometimes we solve for y in order to graph using y equals mx plus b, then substitution makes sense. I think the way this is set up now, I think elimination makes sense because I can multiply the bottom equation by 10 and then eliminate y with subtraction. So multiply by 10, not doing anything to the top equation. 25x plus 50y is 4200. 30x plus 50y is 4800. And subtraction eliminates y. So this is going to be negative 5x. This is going to be negative 600. And when you divide by negative 5, you get negative 600 divided by negative 5, you get 120. So x is 120. All right, so that tells us, and that makes, makes my graph off just a little bit. Maybe the point of intersection was actually here. I just mismarked it. Looks like it's actually supposed to be right there. So we'll just change that. Hard to tell when those two lines blend together, but now we know exactly where it is. So it should be 1, 2, 3, 4, 5, 6. Missed it again. Sorry. Right there. Okay. I think we're good now. All right. So we know the x coordinate, and now let's plug in. We can plug into either one of these, just like typical elimination, replace x with 120 in either one of these and solve for y. And I know this video is getting a little bit long, but if you do that, if you let either one of these x's be 120 and you solve for y, you should get 24. So this point is actually the point 120, 24. And that just leaves us with this bottom point. We know what the y is, no question about that. We know the y coordinate's got to be 10, but we're not completely sure about the x. Can't really tell. The graph doesn't really give us that information. So once again, it's the red equation. If you're thinking of a system, the red equation would be y equals 10, and where it intersects with the green equation, which is 3x plus 5y is 480. Once again, substitution. Y is 10, so 3x plus 50 is 480. 3x equals 430. And 430 divided by 3 is 143.3. All right, so that final vertex right there, bottom right corner, is the point 143.3, and that's the x, and the y is 10. Okay, so I hope that made sense how we utilized past knowledge of solving systems to help us identify these vertices where the graph really doesn't make it plain and obvious. Okay, now we're just about ready to identify our final answer. So I'm going to go back to the previous slide where we have our revenue function, and we're just going to take these ordered pairs. I think you know what to do from here. You're going to plug each of those vertices. There's 4 of them, and the objective of this is to determine how many of each type of package delivered would maximize revenue. So we're looking just for the ordered pair that gives us the highest number, and then we need to tell what that number is. All right. So maybe I'll just leave this part with you. If you'll test each one of your vertices in this. So remember, you're testing these. Let me just go ahead. I'll tell you which one is the maximum, but you go ahead and tell me what the maximum revenue is. And the reason why I'm doing this is because when this comes up, the actual number that gives us the maximum revenue, the ordered pair, is this. It's the combination of 143.3 and 10. Well, these represent number of packages delivered. Obviously, we can't deliver partial packages. So whenever you run into a situation like this, and the ordered pair that does accomplish the maximum or the minimum involves a decimal, please round it. And that just tells me that you understand the context of the problem. So I'm going to go ahead and tell you that this is the ordered pair that creates the maximum revenue, but you need to write your answer as 143 standard packages need to be delivered and 10 oversize. So show me that you understand that you can't deliver partial packages. That's all I'm saying. But go ahead and finish this problem, and next time we meet, I'd like for you to tell me what the maximum revenue number is. Okay, so that's pretty much that problem. We slowed it down a lot. I hope that they don't typically take that long, but I just want to explain as we go. I hope that helps you, but if you have any questions at all, or maybe you have questions about other problems on the homework, feel free to reach out to me, and I will be glad to help you.